Okay, so let us take a new quadratic form. 6x square plus 3y square plus 3z square minus 2yz plus 4zx minus 4xy. You need to reduce this quadratic form into canonical form, and also you need to discuss its nature, and you need to find rank, index, signature, and also you need to write matrix of quadratic form. Okay, so you need to reduce above quadratic form into canonical form by using orthogonal reduction. Okay, and also discuss nature, rank, index, signature of the quadratic form, and also matrix of linear transformation, and also write matrix of linear transformation. Okay, now let us start with taking quadratic form. It is 6x square 3y square 3z square minus 2yz plus 4zx minus 4xy. Okay, now let us find the matrix of quadratic form corresponding to given quadratic form. Let us find matrix of quadratic form. Okay, this will be denoted by A. Since the variables are xyz, so it will be a 3 by 3 square matrix. Okay, now fill the principal diagonal elements. So it will be coefficient of square terms. So square term coefficients are 6, 3, 3. So the principal diagonal will be 6, 3, 3. Now let us assume x as 1, y as 2, and z as 3. Okay, now consider the term minus 2yz. The coefficient is minus 2 divided by 2, it is minus 1. Now place minus 1 in 2, 3 position and 3, 2 position. Okay, this is 2, 3 position and this is 3, 2 position. Now take the next term, it is 4xz, coefficient is 4 divided by 2, it is 2. Now place 2 in 3, 1 position and 1, 3 position. So it is 1, 3 position and it is 3, 1 position. Now the other one is minus 4xy, coefficient is minus 4. It is divided by 2. When it is divided by 2, it is minus 2. Place minus 2 in 1, 2 position and 2, 1 position. So minus 2, minus 2. So it is called matrix of quadratic form. Now you need to consider characteristic equation and find its roots. So characteristic equation has the formula. Characteristic equation is having the formula determinant of a minus lambda equals to 0. Okay, now it will be A is matrix of quadratic form. 6 minus 2, 2, minus 2, 3 minus 1, 2 minus 1, 3. Minus lambda into I is identity matrix of order 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1 into x equals to null matrix. Now subtract corresponding elements. It will be 6 minus lambda minus 2, 2, minus 2, 3 minus lambda minus 1, 2 minus 1, 3 minus lambda into, okay, so there is no capital X here, it is determinant is equals to 0. Now let us expand this 3 by 3 determinant. Now continuation of this step, it is 6 minus lambda into it is 3 minus lambda minus 1 minus 1 3 minus lambda plus 2 into minus of minus 2 plus 2 plus 2 into close second column and row 1, it is minus 2 minus 1 2 3 minus lambda plus 2 into close row 1 and column 3, it is minus 2 3 minus lambda 2 minus 1 is equals to 0. Now let us expand it. It is 6 minus lambda into AD minus BC, it is 3 minus lambda whole square minus 1 2 into minus 2 into 3 minus lambda plus 2 plus 2 into 2 minus 2 into 3 minus lambda is equals to 0. Now it is 6 minus lambda into lambda square plus 9 minus 6 lambda minus 1 plus 2 into minus 6 plus 2 lambda plus 2 plus 2 into 2 minus 6 plus 2 lambda is equals to 0. Now it is 6 minus lambda into lambda square minus 6 lambda plus 8 plus 2 into 2 lambda minus 4 plus 2 into minus 4 plus 2 lambda is equals to 0. Then it is 6 lambda square minus 36 lambda plus 48 minus lambda cube plus 6 lambda square minus 8 lambda 4 lambda minus 8 plus 4 lambda is equals to 0. Now it is minus lambda cube 6 lambda square 12 lambda square 4 lambda plus 4 lambda 8 lambda. So lambda coefficient is minus 36. Then 48 minus 16, it is 32 plus 32 is equals to 0. Now let us continue from this step. So there are two ways to find the roots of third degree equation. So let us apply synthetic division method. Okay. The characteristic equation is minus lambda cube plus 12 lambda square minus 36 lambda plus 32 equals to 0. Let us start with lambda equals to 1. Substitute lambda equals to 1. It will be minus 1 plus 12 minus 36 plus 32. It is minus 37 plus 44. Minus 37 plus 44 is not 0. So 1 cannot be a root. Now let us start with 2. It is minus 8 plus 12 into 4, 48. 72 plus 32. It is 48 plus 32, 80. 80 minus 80 is 0. Since 2 satisfies this equation, so by remainder theorem, lambda minus 2 is a factor here. Okay. Now let us identify other factors using synthetic division. Right from highest coefficient to lowest coefficient. It is minus 1, 12, minus 36, 32. 0, add these two, minus 1, multiply these two, it is minus 2, 10, multiply these two, 20, multiply these two, minus 32, 0. Now the factors are lambda minus 2 minus lambda square plus 10 lambda minus 16 is equals to 0. Now let us find the other factors. Lambda minus 2 into minus lambda square plus 8 lambda plus 2 lambda minus 16 equals to 0. It means lambda minus 2 into, take minus lambda common, lambda minus 8, take 2 common, lambda minus 8 is equals to 0. Now lambda minus 2 into lambda minus 8 into minus lambda plus 2 equals to 0. So the roots are 2, 2, 8 are the eigenvalues of A. Okay, 2 to 8 are the eigenvalues of A. Now let us find the eigenvectors corresponding to 2 and 8. Okay, so now let us find the eigenvector corresponding to eigenvalue 2. Okay, eigenvector is not a null matrix satisfying the equation A minus lambda E into capital X equals to null matrix. So here A minus 2I is 4 minus 2, 2 minus 2, 1 minus 1, 2 minus 1, 1 into X equals to null matrix. Okay. Now let us apply echelon form method in order to solve. Okay. So apply the operation R2 plus 1 by 2 R1 and R3 to R3 minus 1 by 2 R1. It will be 4 minus 2, 2. So minus 2 plus 2, 0, minus 1 plus 1, 0, minus 1 plus 1, 0, 2 minus 2, 0, minus 1, minus of minus 1, 0, 1 minus 1, 0. Now by back substitution, it is in echelon form. By back substitution, you got 4x minus 2y plus 2z equals to 0. Let us consider a difference. It has two terms. One is number of unknowns. The other one is rank of coefficient matrix. Unknowns are x, y, z. Number of unknowns are 3 and rank is 1. Difference is 2. This difference is saying that you need to suppose two unknowns so that other can be easily evaluated. Let us suppose z as k1 and y as k2. So you will have 4x minus 2 k2 plus 2 k1 equals to 0. Then x equals to k2 minus k1 by 2. So you got the eigenvector as x equals to xyz and it is k2 minus k1 by 2. The other are k2, k1. It is the eigenvector corresponding to 2. Now let us find the other eigenvector corresponding to 8. Okay. Again, eigenvector is not a null matrix satisfying the equation A minus lambda I. Here lambda I is 8 into x equals to null matrix. Okay. Let us write A minus 8i. It is 6 minus 8 minus 2. 3 minus 8 minus 5. 3 minus 8 minus 5. Now let us apply echelon form method. So in order to move further, apply the operation R2 to R2 minus R1 and R3 to R3 plus R1. Make use of diagonal elements. It is minus 2, 2, 0, minus 2, minus 5 plus 2, it is minus 3, minus 1, minus 2, minus 3, 0, minus 3, minus 3. So this is possible diagonal. Still you need to make minus 3 as 0. Let us apply the operation R3 to R3 minus R2. It will be minus 2, 2, 0, minus 3, 0, 0, 0 into capital X is equals to null matrix. Now it is in echelon form method. Then apply back substitution. by back substitution, the system of equations are minus 2x minus 2y plus 2z equals to 0 and minus 3y minus 3z equals to 0. Now let us consider a difference. It is number of unknowns minus rank. Unknowns are 3, x, y, z. So number is 3. Rank of coefficient matrix is 2. Difference is 1. So 1 is saying that you need to suppose one unknown. Let us consider z as k3. Then y will be minus k3. So minus 2x minus 2 into minus k3 plus 2k3 is 0. Then minus 2x plus 2k3, it is 4k3 is equals to minus 4k3, then x equals to 2k3. So finally eigenvector is xyz, it is 2k3 minus k3, k3 is eigenvector of lambda equals to 8. Now we need to verify all the three eigenvectors are mutually orthogonal or not. If it is not satisfied, if that mutually orthogonal condition is not satisfied, you need to take a new vector ABC and you need to assume that it is orthogonal to other two vectors and you need to evaluate it. So let us assume particular values to k1, k2 and k3. I suppose k1 as 1, k2 as 1, so that the eigenvector is not a null matrix. So I have taken k1 as 1, k2 as 1. It will be 0, 1, 1. So I have taken k1 and k2 as 1. You can take any value so that the eigenvector is not a null matrix. Here I will take k3 is also 1. It will be 2 minus 1, 1. So that eigenvector is not a null matrix. Okay. Now the first eigenvalue is 2. The corresponding eigenvector is x1 given by 0, 1, 1. The next eigenvalue is also 2 and corresponding eigenvector is also same, that is 0, 1, 1, and last eigenvalue is 8. Corresponding vector is 2 minus 1, 1. Let us name it as x3. Okay, 2 to 8 are eigenvalues. These are corresponding eigenvectors. Okay, the important point in orthogonal reduction procedure is all the three eigenvectors must be mutually orthogonal. So let us check that condition. Apply orthogonal condition on these two. It will be, if it is a1, b1, c1, a2, b2, c2, you must satisfy a1, a2 plus b1, b2 plus c1, c2 is 0. It is 0 plus 1 plus 1, sum is 2, 2 cannot be 0, hence these two are not orthogonal. Now let us apply the condition on x2 and x3. If it is a1, b1, c1, a2, b2, c2, you must satisfy a1, a2 plus b1, b2 plus c1, c2 is 0, that is 0 minus 1 plus 1, it is 0, hence these two are orthogonal. Now apply the condition on the first and last. It will be 0 minus 1 plus 1. The sum is 0. Hence 1 and 3 are also orthogonal. So 1 and 2 are not orthogonal. 2 and 3 are orthogonal. 1 and 3 are orthogonal. Hence here mutually orthogonal condition is not satisfied. So in such a cases, you need to assume one of the eigenvector as ABC and assume it is orthogonal to two other vectors so that all the eigenvectors are mutually orthogonal. So here mutually orthogonal condition is failed. So let us assume one of the eigenvector as ABC and it is orthogonal to other two vectors. Now x1 is orthogonal to x2. x1 is ABC, x2 is 0 1 1 0 1 1. Okay, on applying orthogonal condition you will get 0a plus b plus c equals to 0. It is a1 b1 c1 and it is a2 b2 c2. Orthogonal condition is a1 a2 plus b1 b2 plus c1 c2 is 0. Now let us take x1 and x3 are orthogonal. Now you will get 2a minus b plus c equals to 0. Now let us find ABC values in shortcut method. A by determinant minus b by determinant, c by determinant. Now close first column, it will be 1 1 minus 1 1. Close second column, it is 0 1 2 1. Close third column, 0 1 2 minus 1. It is a by 1 plus 1 2, b by 0 minus 2, it will be plus 2, and c by 0 minus 2, it is minus 2. Now the required eigenvector is 2 2 minus 2. It is eigenvector of 2, so that it is orthogonal to other two eigenvectors. So let us verify whether these three are mutually orthogonal or not. Okay, so consider x1 and x2, apply the condition, orthogonal condition. It is 0 plus 2 minus 2 0. Okay, take 2 and 3, it is 0 minus 1 plus 1, sum is 0. Take 1 and 3, it is 4 minus 2, sum is 0. Hence all the three vectors are mutually orthogonal. Okay, so this is the important verification. All the three vectors must be mutually orthogonal. Okay, then let us form model matrix. It is denoted by P. It will be 2 2 minus 2. It is the eigenvector corresponding to 2. The next eigenvector 0 1 1. This is the eigenvector corresponding to 2. And the last eigenvector 2 minus 1 1. This is the eigenvector corresponding to 8. Now form normalized model matrix. It is P cap. This is equals to, let us find length of the column. It will be root over 2 square plus 2 square plus minus 2 whole square. It is root over 4 plus 4 plus 4. It is root 12. Now divide each element by its length root 12. So it is 2 by root 12, 2 by root 12 minus 2 by root 12. Now take the second column. The length is root over 0 square plus 1 square plus 1 square. It is root 2. Divide by root 2. It is 0, 1 by root 2, 1 by root 2. And the last one, the length is root over 4 plus 1 plus 1, root 6. Divide by root 6, it will be 2 by root 6 minus 1 by root 6 and 1 by root 6. Okay, so P cap is equals to 2 by root 12, 0, 2 by root 6, 2 by root 12, 1 by root 2, minus 1 by root 6, and minus 2 by root 2, 1 by root 2, 1 by root 6. Just divide with its length. Now let us start with quadratic form. The quadratic form is 6x square plus 3y square plus 3z square minus 2yz plus 4zx minus 4xy. Let us assume this expression as 1 by 1 square matrix. So it can be represented in matrix notation by x transpose Ax, where x is the column matrix xyz, A is the matrix of quadratic form. Now take the substitution. X equals to P cap y, where P cap is normalized model matrix and y is the column matrix y1, y2, y3. On simplification, you will get something into y1 square plus something into y2 square plus something into y3 square. The brackets can be filled with corresponding eigenvalues. So first eigenvalue is 2, the next eigenvalue is 2, and the last eigenvalue is 8. So required canonical form is 2y1 square plus 2y2 square plus 8y3 square. Okay, on simplifying x transpose ax with the help of x equals to p cap y, we will get the canonical form 2y1 square plus 2y2 square plus 8y3 square. The coefficients are just eigenvalues of the matrix of quadratic form. Now you got the canonical form. So few more questions are there. First one, nature of quadratic form. So all the eigenvalues are positive, hence the nature is positive definite. All the eigenvalues are positive, so nature is positive definite. Okay, next you need rank. You need rank of quadratic form. So rank of quadratic form is number of non-zero terms in the corresponding canonical form. Number of non-zero terms are 3, hence rank is 3. Rank is number of non-zero terms in the canonical form, it is 3. Then index. Index of quadratic form, it is number of positive terms in the canonical form. Positive terms are 3. Then you need signature. Signature is difference between number of positive terms and number of negative terms. Positive terms are 3 and there are no negative terms in the canonical form. Okay, number of positive terms in the canonical form are 3, number of negative terms in the canonical form are 0, difference is 3, hence signature is 3. Okay, and the last question, matrix of linear transformation. So matrix of linear transformation is x equals to p cap y, that is matrix of linear transformation. Okay, where x equals to column matrix xyz and p cap is normalized model matrix. Okay, and y is the column matrix y1, y2, y3. Okay, so we have done quadratic form conversion into canonical form with the help of orthogonal reduction. Okay, this comes under, all these topics comes under matrix of this comes under eigenvalues and eigenvectors. Okay, so the applications of eigenvalues and eigenvectors, or eigenvalues and eigenvectors, can be used in finding Google space rank. Google space rank can be evaluated using eigenvalues vectors. Then it can be used in RLC circuits. It can be used in car stereo systems, and it can be used in exploring lands for oil resources, and it can be used in communication systems. Okay, these are all applications of eigenvalues and eigenvectors. Thank you.